view synthesis and relighting have a lot of real-world applications, such as phototourism, VR, and data generation for machine learning. However, existing techniques can handle both tasks simultaneously, impose too many constraints, or have noticeable flaws. Neural light transport for relighting and view synthesis introduces several concepts to address these challenges. A unified framework that integrates directional or image-based relighting and view synthesis, a residual learner scheme on top of a physically correct diffuse base, and a neural method for interpolating the 6D light transport function. The problem can be visualized as interpolating a light transport function to determine the variances at the given location x on the surface, considering the incoming light direction omega I and the viewing direction omega O. This forms a 6D function that outputs RGB colors. To modify both views and lighting, it's possible to create a novel scene view and then relight it. Inspired by geophotography's concept, the cameras and lights share fundamental principles. This paper is treated equally, which enables the creation of a unified framework for view synthesis, relighting, or do both simultaneously. We gather the data using a light stage from multiple cameras, with each light sequentially activating while the subject remains stationary. The resulting images serve as samples of the 6D light transport function. By interpolating between physical lights, we relight the scene with virtual lights. By interpolating between physical cameras, we synthesize novel views using virtual cameras. Doing both operations enhances the resolution of the light stage in terms of both cameras and lights. From the light stage data, we can compute Lambertian diffuse render. It offers a basic representation of diffuse reflection and shading based on physical properties, but lacks many light transport effects of the full render. The NLT network bridges the gap between full rendering and Lambertian base by predicting non-diffuse residuals. Predicting residuals instead of defining RGB colors allows the network to focus on learning complex higher-order light transport effects like specularities and global illumination. Meanwhile, the diffuse render provides base colors and physically accurate arc shadows. By embedding the function into UV space computed from a geometry proxy, we handle viewpoint changes, providing light and viewing directions as cosine maps. The network predicts RGB values for each texel and then resamples the predicted texture map to the camera's perspective for comparison with the ground truth. Additionally, we provide a physically correct diffuse-based rendering to the network to avoid learning albedo and dark shadows from scratch. An observation path encodes non-diffuse residuals for neighboring observed lights and views, output to handle arbitrary numbers of observations. Since the network cannot generalize learnings of complex light effects from one object to another, we must gather a dataset and train the model on it for each object individually. For each task, the dataset is taken differently. For relighting, we get images with different light directions and a fixed viewpoint. For view synthesis, we get images with different viewpoints and a fixed light direction. For simultaneous relighting and view synthesis, we get images into many different viewpoints and light directions. Model prediction adds specularities and global illuminations to the diffuse base. It also compensates for geometric inaccuracies, which means that the method doesn't require perfect geometry. A geometry proxy is enough. Renderings produced by this approach synthesize shadows and specular highlights with higher precision when compared to state-of-the-art algorithms. Inferred residuals produced by NLT can account for the non-diffuse, non-local light transport and mitigate the majority of artifacts in the diffuse base caused by geometric inaccuracy. When compared with the state-of-the-art view synthesis method, NLT exhibits accurate specularities and sharper details, as it can capture view-dependent effects. The method accurately models shadows and global illuminations, by correctly capturing high-frequency details such as specular highlights. In contrast, the state-of-the-art view synthesis model that was extended to support relighting struggles at creating hard shadows due to the lack of the physical shadow modeling. For more examples and detailed insights, please refer to the paper linked in the description below. Thank you for watching.